Welcome to this presentation on query optimization, specifically clustered and non-clustered indexes. This presentation is for the Health Administration and Policy Course 709 at George Mason University. So what is an index? An index is used to speed up a query process in SQL Server, resulting in high performance. An index is similar to a textbook index. In a textbook, if you need to go to a particular chapter, you go to the index, find the number of the page in the chapter, and go directly to that page. Without an index, the process of finding your desired chapter would have been very slow. The same applies to indexes in databases. Without an index, a database management system has to go through all the records in the table in order to retrieve the desired results. This process is called table scanning and is extremely slow. On the other hand, if you create indexes, the database goes to that index first and then retrieves the corresponding table records directly. So an index is an on-disk structure associated with a table or view that speeds up retrieval of rows from the table or view. An index contains keys built from one or more columns in the table or view. And these keys are stored in a structure that enables SQL Server to find the row or rows associated with the key values quickly and efficiently. There are two types of indexes that we will go through in this presentation, which are clustered and non-clustered indexes. A clustered index defines the order in which data is physically stored in a table. Table data can be stored in only one way, therefore there can be only one clustered index per table. In SQL Server, the primary key constraint automatically creates a clustered index on that particular column. Clustered indexes sort and store the data rows in the table or view based on their key values. These are the columns included in the index definition. And there can be only one clustered index per table because the data rows themselves can be stored in only one order. The only time the data rows in a table are stored in sorted order is when the table contains a clustered index. When a table has a clustered index, the table is called a clustered table. If a table has no clustered index, its data rows are stored in an unordered structure called a heap. Let's review some of the benefits of a clustered index. The data in a clustered index is stored in order, which means that finding the data you need in your clustered index is a matter of knowing where to look in the alphabetical list of data. Computers are really good at doing this. If your data needs to be outputted in the same order that it's stored in, then SQL doesn't need to do any additional sorting. A lot of people like to put the clustered index on their table's primary key. And this is usually fine because a lot of the time our primary key is likely to be our most used field for joins, where statements, etc. Some people think they can only put their clustered index on their primary key, and that's not true. Oftentimes, it can be much more beneficial to put your clustered index on something that isn't your primary key, like a different column that is getting more use than our primary key. Another major benefit of a clustered index is that we don't have to include any additional data in our index. All of the data for our row exists right beside our index columns. And finally, a great feature of clustered indexes is that if you ever need to retrieve many or all columns from your table, a clustered index will usually be efficient because once it finds the index value you're searching on, it doesn't need to go anywhere else to get the remaining data from that row. Moving on, let's now discuss non-clustered indexes. A non-clustered index doesn't sort the physical data inside the table. In fact, a non-clustered index is stored at one place and table data is stored in another place. This is similar to a textbook where the book content is located in one place and the index is located in another. This allows for more than one non-clustered index per table. And it's important to mention that inside the table, the data will be sorted by a clustered index. However, inside the non-clustered index, data is stored in the specified order. The index contains column values on which the index is created and the address of the record that the column value belongs to. When a query is issued against the column on which the index is created, the database will first go to the index and look for the address of the corresponding row in the table. It will then go to that row address and fetch other column values. It is due to this additional step that non-clustered indexes are slower than clustered indexes. Non-clustered indexes have a structure separate from the data rows. A non-clustered index contains the non-clustered index key values, and each key value entry has a pointer to the data row that contains the key value. The pointer from an index row in a non-clustered index to a data row is called a row locator. The structure of the row locator depends on whether the data pages are stored in a heap or a clustered table. For a heap, a row locator is a pointer to the row. For a clustered table, the row locator is the clustered index key. You can add non-key columns to the leaf level of the non-clustered index to bypass existing index key limits and execute fully covered indexed queries. Let's discuss some of the benefits of a non-clustered index. First, we can have as many non-clustered indexes on our tables as we want. However, there's overhead in creating non-clustered indexes. Essentially, every time you index some column or columns, you're duplicating the unique values in those columns so that they can be stored in sorted order in your index. We get speed and efficiency in our data lookups, but with the cost of losing disk space. You need to test and see for each table and set of queries what the optimal number of indexes are. Adding an additional index can absolutely destroy performance, so always test your changes. Additionally, using a non-clustered index to find an index column's value is fast. SQL is just going through the ordered index data to find the value it needs. Again, something computers are really good at doing. However, if you need other columns of data from the row that you just looked up, SQL is going to have to use those index pointers to go find the rest of that row data somewhere else on the disk. This can really add up and slow down performance. If those additional lookups are hurting performance, what you can do is include your non-indexed columns in your non-clustered index. What this basically does is, in addition to storing the sorted values of your index columns, the index will also store whatever additional values you want to include as part of the index itself. Again, you'll probably get better performance because SQL won't have to go somewhere else on the disk to find the data it needs, but you'll lose storage space because you're creating duplicates of that data as part of your index. A couple other key points I want to be sure to make are that both clustered and non-clustered indexes can be unique. This means no two rows can have the same value for the index key. Otherwise, the index is not unique and multiple rows can share the same key value. Indexes also are automatically maintained for a table or view whenever the table data is modified. Indexes are automatically created when primary key and unique constraints are defined on table columns. For example, when you create a table with a unique constraint, Database Engine automatically creates a non-clustered index. If you configure a primary key, Database Engine automatically creates a clustered index, unless a clustered index already exists. When you try to enforce a primary key constraint on an existing table and a clustered index already exists on that table, SQL Server enforces the primary key using a non-clustered index. Let's review how indexes are used by the Query Optimizer. Well-designed indexes can reduce disk operations and consume fewer system resources, therefore improving query performance. Indexes can be helpful for a variety of queries that contain select, update, delete, or merge statements. When a query is executed, a Query Optimizer evaluates each available method for retrieving the data and selects the most efficient method. The method may be a table scan or may be scanning one or more indexes if they exist. When performing the table scan, the Query Optimizer reads all the rows in the table and extracts the rows that meet the criteria of the query. A table scan generates many disk operations and can be resource intensive. However, a table scan could be the most efficient method if, for example, the result set of the query is a high percentage of rows from the table. When the Query Optimizer uses an index, it searches the index key columns, finds the storage location of the rows needed by the query, and extracts the matching rows from that location. Generally, searching the index is much faster than searching the table because, unlike a table, an index frequently contains few columns per row and the rows are in sorted order. The Query Optimizer typically selects the most efficient method when executing queries. However, if no indexes are available, the Query Optimizer must use a table scan. Your task is to design and create indexes that are best suited to your environment so that the Query Optimizer has a selection of efficient indexes from which to select. Let's next discuss a few scenarios. In this first scenario, you have a query that wants to return most or all of the columns from a table. What type of index would make this the most efficient? The answer is a clustered index. Since all of the column values are stored in the same location as your indexed fields, SQL won't have to do any additional lookups to get all of the data you're requesting from it. If you created a non-clustered index, you would have to include all non-indexed columns, which would take up lots of space since you are essentially duplicating your entire table's data. In this second scenario, you have a table that is constantly having values updated. These updated values are used in your joins and where clauses. What type of index would you add? The answer is a non-clustered index. If our values are constantly changing, SQL only has to update the index and pointers while putting the actual data wherever it has available space on the disk. Compare this to a clustered index where it has to put the inserted or updated data in the correct order, meaning potentially lots of operations to shift the data around if available free space doesn't exist at that location. In our final scenario, you have a table that already has a clustered index, but it doesn't cover columns and joins and where clauses. What do? The answer is create a non-clustered index. Since the clustered index already exists, your only option is to add a non-clustered index. Depending on the queries hitting this table, however, you may want to consider changing your clustered index to a non-clustered index if you think your joins and where clauses will be improved by having those fields be part of the clustered index. Thank you for taking the time to review this presentation. If you would like to learn more, please see the following references.